Okay, fine. Now we will move on to the next strategy. Of solving the computation, solving any computation problem, which is known as greedy method. So divide and conquer is one strategy. Greedy method is another strategy. Now, let us first try to understand what this method is. What is the approach of this method? Then let us try to consider we have a problem P. P is a problem. Just like in divide and conquer, we have seen P is a problem, how that problem is divided. The same way here also we have a problem P which we want to solve. Now, for example, let us consider that this is a problem of solving a payment option. As an example, we are taking when buying a product. Now, what all solutions are there for this, or what is the input, so that we can find the solution for those inputs? There may be n number of inputs. Perform payment. We can have exercise the option of cash on delivery. That is one of the solution. We can pay by debit card. We can use credit card. We can use a PayPal, or we can perform online bank transfer. Now, okay, we can also have checks also, the last option. So there is a problem P, and for that we have n inputs to solve that problem. And for example, here we have some inputs. And there is also some constraint. Now, let us, for example, take the constraint. Those constraints are applied on these inputs. Now, let us say that in this case, the first constraint is seller, they do not accept checks. So there is no way a customer can pay by using checks. And the other constraint is that there is no cash on delivery option available. Though cash on delivery and checks is one of the solutions there for making a payment. But the constraint is that seller does not accept checks and seller does not accept cash on delivery. So what happens now? Among these solutions, cash on delivery cannot be exercised. Check cannot be exercised. So there is no way we can use these two solutions to have to make a payment. Then what all solutions we are left with? The payment through debit card, credit card, PayPal, and online bank transfer. These solutions are known as feasible solutions. They are feasible. Cash on delivery and check was not feasible because of the constraint there. So these are feasible solutions. So for a problem, there can be any number of feasible solutions. But we want something better among these feasible solutions. Though you can use any of the solution and payment can be done. But what we want is we want some optimization. We want a better solution among these feasible solutions. So let us consider there are few other things. A debit card or credit card, if we have to make the payment through debit card and credit card, let us consider that 1.5% is the transaction fees. That is what is extra when we, if we use them. And bank transfer will attract 2% extra. Extra fees. PayPal, whereas assume that it is free. There is no transaction fees required for PayPal. So, what is the best solution in this case? Best solution is using PayPal because it doesn't cost more because of the transaction fee. And this solution is known as optimal solution. Among feasible solutions only, one of the solution will be an optimal solution. Now, why we say that, now you can understand the term greedy, why this strategy is called as a greedy method, or this approach is known as greedy method. Greedy, I mean, we try to find something much better, which is cost effective. That is what is the greedy method. So instead of using debit card or credit card, we will be selecting or we will be exercising the option of PayPal, which cost us less. So that is why the term is greedy. We want something better with less cost. Now, it's not always the less cost. Some problems we need to look at the profits there, more cost, more profits. So actually what happens is an optimal solution, whatever is selected, will either minimize or maximize the objective function. Now in this scenario, what is our objective function? Our objective, or what is our objective? My objective over here is to make a payment uh, which does not attract extra overhead or extra fees. That's my objective function. And here the problem is minimization. I want to minimize my payment amount. But an optimal solution is a solution which minimizes or even maximizes the objective function. So this was an example that we have a problem. We may have several solutions, but some solutions might not be feasible at all. Some solution will be feasible and feasible based on some constraints. And those feasible solutions, among those feasible solutions, we will have an optimal solution which will minimize and maximize the objective function. Now, the problem is about using the greedy method, greedy approach. There are n inputs. Those are nothing but can be solutions. Among those n inputs, there will be solutions. Then our purpose is to find a subset of the inputs, that is among n, some subset which satisfies some constraints. The inputs are the subset of inputs that satisfies the constraints. They are known as feasible solutions. And among this feasible solution, we need to find a feasible solution that maximizes or minimizes an objective function. This is known as an optimal solution. So always our purpose, our approach using greedy method would be to find an optimal solution. Now let us try to look at the general method of greedy, which is also known as control abstraction for greedy method. Now there is A, obviously there are n number of inputs, and all these inputs are stored in an array A. Now initially we take the solution set as null. There is nothing in the solution. Solution means a feasible solution. So there is nothing in the solution right now. Now we try to take each input, that is an input. So we have a loop from 1 to n and select that input from the array A, and check if that input which is selected, which is x now, is a feasible solution. If it is feasible, then add to the set of the feasible solutions, that is solution set. So we make use of union operation, union solution comma x, that is solution was null, x is added to the solution. Next time another input is selected, and if that input is feasible, then it will be added to the solution set, otherwise it will not be added, discarded. Then once this for loop completes, at the end we return the solution which will have all the feasible solutions. Now remember, here we are not right now concerned about the optimal solution because we do not know what is the objective function. So here the general algorithm for greedy is to have a null solution, and among the inputs select each input at a time, I check whether it is feasible. If it is feasible, add to a solution set and return that solution set. There are several algorithms that can be solved uh, using this greedy approach. The most common is the knapsack problem. Then we have job sequencing with deadline, minimum cost spanning trees, optimal storage on tapes, optimal merge patterns, and single source shortest path. Now, among these uh, problems that can be solved, what we have is we only have knapsack, job sequencing with deadline, minimum cost spanning tree, and single source shortest path as part of your whatever is mentioned in your syllabus. Optimal storage on tapes and optical merge pattern is not is mentioned in your syllabus. So we will be looking at these problems, that is knapsack, job sequencing with deadlines, and minimum cost spanning tree, as well as single source shortest path. Now before we move, what we will actually do in these problems is we will determine a feasible solution. So we will have many number of feasible solutions, and a feasible solution may or may not be optimal. Our goal of solving this problem would be to minimize or maximize, depending upon the problem, minimize or maximize the objective function. And this approach works in stages actually. At first stage, we select an input. Second, examine that input, and we will look at whether it gives us the optimal solution or not. And then next stage, we again try to select another input and try to see whether it increases the cost or decreases the cost, or whether it maximizes or minimizes the objective function. Then select it or discard it. So ultimately, what happens is the last stage, the all the inputs, whatever I mean, all this among all the inputs, whatever solution we get, we say that that will be an optimal solution. And the comparison or feasibility to check whether it is feasible and optimal or not. Since the objective function tries to, using the objective function, we try to achieve some objective. So always it is the local choice which is made on the input. So when we have an input, we see whether locally it optimizes or not, and then include in the solution and continue until all the inputs are done, or until we find the solution itself. So this is what is all about the explanation about the greedy method. Now let us look at applications of this greedy method. We will apply these greedy methods, greedy method on several problems. So our first problem would be the knapsack, which is very, classical, or what we say, a very commonly used problem. Solved using the greedy approach. Just let me. Okay. Okay. Now, first of all, let us try to understand what this what this knapsack problem is. Then we will look at how to apply the greedy approach to get the optimal solution. Now, actually, knapsack, we have n number of objects. Let us consider we have 3 objects as an example. Object 1, object 2, object 3. Let's say object 1 is oranges, object 2 is apples, object 3 is bananas. Now, in some textbooks, there is an example taken of object 1 as gold, object 2 as silver, object 3 as diamonds. But anyway, let us try to use a common entities there. Oranges, apples, and bananas. Then each object, there is some weight associated with each object. And Along with the weight, there is some profit associated with each object. That is the value of that object, actually. So, in a set, when we have three objects, let's say W1, W2, W3 represents the weight of object 1, object 2, object 3, which is 18, 15, and 10. This weight can be in kgs, can be in anything, pounds or lbs or anything. With this, we have profits P1, P2, P3 for object 1, object 2, object 3 respectively. That is 25, 24, 15. This can be rupees, dollars, or any unit. Now, there is a bag given. That is what is known as a knapsack. There is a sack or a knapsack we have, and there is a capacity to this knapsack. Let's call this capacity as M. Now the thing is, we have the objects. Objects has weights and profits, and there is a bag known as knapsack which has a capacity. Let's call that capacity as M. Now what is the purpose is that, let us consider, for example, as we consider three objects, capacity of the knapsack is 20. Now the purpose or the problem is that here we have to fill the problem statement. If you read, we have to fill this knapsack with the objects that maximizes the total profit. What is the capacity of the knapsack? M. Now, if there is large capacity in the knapsack, which could fill up all objects M, object 1, object 2, object 3, then there would not be any problem at all. For example, what we have to do, we need to put object 1 in the sack, like all oranges, let's say, all apples, all whatever the third one, bananas was. So here what we are doing is all these objects has to be filled in the knapsack to earn maximum profit. But can we fill this knapsack with all these objects? For example, object 1 has weight, filling all the objectives. Object 1 has weight 18, object 2 has weight 15, object 3 has weight 10. So W1 plus W2 plus W3, that is the weight of all these things, because if you have to fill all these objects inside the knapsack, its weight together will be 43, which is much larger than the size of the knapsack or the capacity of the knapsack, which is 20 kgs. So 43 cannot fit in 20 kgs. So again, going back to the problem statement, what we have to do, we have to fill the knapsack. So problem statement doesn't say that we have to fill the knapsack with all the objects to get maximum profit. I mean, filling all getting maximum profit doesn't make sense. There is a capacity. So we have to fill the knapsack with these objects to earn a higher profit. Now let us look at how we come to the part here. What we do is we say there is something known as x1, x2, and x3. X is nothing but fraction. What will be the fraction? We have a question marks here because we don't know what fraction x1, x2, x3 will have. We have fractions of the weights, that is W1, fraction x2 of weight W2, fraction x3 of weight W3. So we don't fill with the whole weight. We fill the knapsack with some fraction of the weight x1, fraction of weight x2, fraction of weight x3, so to earn maximum profit. Now what fraction means? Part. So instead of taking 18 kgs, we can just fill that with 10 kgs also. And instead of taking whole 15 kgs of object 2, we can fill it with 5 kgs also. But the ultimate object is to earn maximum profit. So x1, x2 are nothing but fractions of the weights. So using this scenario, the logic here. We come to the a formula. Let us consider W1. We already know, we have seen W1 plus W2 plus W3 should be equal to M. We have said that, but it was greater, so we rejected that hypothesis. Now what we say is fraction of weight. So it is W1 of X1. How much of object 1 is put in the bag, in the knapsack, plus fraction of W2, weight, fraction of W2 with weight 2. So how much is object 2 put in the bag? Plus W3 into X3, that is how much fraction of X3 into the weight is put in the bag. Summation of all these things should be less than equal to M. That is the constraint. It should be the whatever, how much ever the objects, object 1, object 2, object 3 selected, it should be less than equal to the capacity of the knapsack, which is M. That is actually the constraint. We cannot fill the knapsack with more than its capacity. So if we generalize this formula, what we get is we have summation of weight with its fraction should be less than equal to M. It should be less than equal to M for I 1 to N. 1 to N. What is N? N is the number of objects. So for each object I, summation of W1 and X1 should be less than equal to M. And what is the range of X? X can be, the range is from 0 to 1 because it's fraction. Half. Suppose instead of 18, I want to fill this with 9. That means fraction is 1 by 2, half. So the range of fraction X lies between 0 to 1. 0 means no, that nothing of that object is filled. And 1 means whole of the weight. So if we multiply, if X is 1, so X1, 1 means 1 multiplied by W1 is 18, means all 18. The whole of the object 1 is filled. So X lies between 0 to 1. Now, then what is the profit earned? Profit earned would be, instead of fraction multiplying with the weight, fraction we have to multiply with the profit, because that much profit will be earned. So P1 X1 plus P2 X2 plus P3 X3 will give us the total profit. And X1, X2, X3 are fractions, P1, P2, P3 are the profits. What we will achieve by putting those fraction of the weights. Now, if we generalize this P1, P2, P3 and X1, X2, X3 for n number of objects, then what we have is summation of Pi Xi, where I lies between, again, 1 to n. Xi is between 0 to 1. That's what we have seen. Now, what is the objective then? Summation of Pi Xi is the total profit. Objective is to maximize the total profit. So we have, this problem is maximization, not minimization problem. This is known as maximization problem. For example, the general example what we have considered for the greedy method of payments, options of payments, debit card, credit card, and PayPal. There, PayPal was free, so we wanted to spend less amount of money, so that was a minimization problem. Now here, this is a maximization problem because we want to earn maximum profit by putting object 1, object 2, object 3 in the full object or part or fraction of this object. So let us continue further. So what will be the just a second. ये चेक करा लिया क्या? पता? हाँ लिखा लिया। शरीफ साहब ही लिखे। शरीफ साहब। हाँ, वो हिसाब से हो रहा था। एक बार दो। नहीं होगा, नहीं कह के बोले तो क्या हो जाता, ये फिर करेक्शन में गड़बड़ हो जाती। आज क्या है इसकी जरूरत नहीं, ये ऑफिस की नहीं थी भाई। हाँ नहीं, सुनो सुनो सुनो, एक चीज सब रिकॉर्डर में क्या करना है, नहीं नहीं, जब आप ये साइन करा लेते ना, तो ये शरीफ साहब को देखने के वास्ते छे। अब क्या करते शरीफ साहब, ये देख लेते ना, अब इन्हों यहाँ पे साइन करते, करेक्शन समझ रहे, इन्हों यहाँ पे साइन कर दे, ये बेकार हो जाती है, तो ये निकाल देना था, खाली ये रखना था आप। अब बाकी का कट्टा रहना था अपने पास। ठीक है, चलो शुक्रिया। Okay, sorry for that. I mean, some administrative work had come up. So anyway, doesn't matter. Let us continue with the problem. Now, what do we do? How do we proceed with solving this problem? Remember, we have to get maximum profit. And the constraint is this x1, x2, x3, whatever summation of wi and xi should be less than equal to m. So let us first consider the objects in the series of maximum weight. Maximum weight. So what I mean is, if we select the object in sequence of maximum weight, then we'll be able to fill knapsack with it, and we may earn a larger profit. So what do we have now? Maximum weight means object 1, object 2, object 3. Here we have weight 18, 15, and 10. So if what is the maximum weight? 18. 18. Let us fill this object. Let us fill whole bag with 18. So when we fill the whole bag with 18, what is the fraction? 1. 1. If the whole weight we are filling the bag with object 1. So 1. Fraction x1 will be 1. So when x1 is 1 and filled, knapsack has the capacity 20. My 18 is filled with object 1. How much is remaining? 2 kgs. So now we can fill 2 kgs of object 2 or object 3. And our criteria was to select the object with highest weight. So let us select 15 because 10 is lower than 15, 15. But can we fill the knapsack with a total 15? No, only 2 kg is left. So what will be the fraction? Fraction will be the remaining amount, capacity that is remaining, 2 divided by the weight will give us the fraction. Because we can only fill up 2 kgs of object 2. So the fraction x2 will be 2 by 15. Then 2 kgs of object 2 is filled up, remaining capacity is 0. So can we fill it with object 3? No. So fraction of object 3 is 0. Are we satisfying the weight? Let us compute summation of wi xi. 1 with the weight 18 is 18 plus 2 by 15 with 15. So 15, 15 get cancelled. We have 2. So 18 plus 2 is 20 plus 10. That is the weight, and fraction is 0. So 0 is equal to 20. So we are satisfying this constraint. Now let us try to compute its profit. Profit means we have to take P1, P2, and P3 with its fraction. Fraction we know 1, 2 by 15, and 0. So let us compute the fraction, the profit. Profit is summation of Pi and Xi. Now we are not bothered whether it is maximum or not. We are just computing the total profit earned. So 1 multiplied by profit P1 is 25, sorry, and 2.5, which is a fraction, multiplied by 24 is 24 and 2.5, and then 0 multiplied by 15 because nothing of object 3 is filled, x3 is filled. That will give us the total profit of 28.2. So let us write it over here, 28.2. 2. Now then, the next thing is, what did we achieve? This constraint was satisfied, 20. The knapsack is filled with 20 kgs, complete whole knapsack is filled. Fraction object of x1, the whole object of x1 is, uh, filled in the knapsack. 2 by the ratio of 2 by 15, fraction of 2 by 15 of object 2 is filled, and nothing of object 3 is filled, which gives us the profit of 28.2. Now, this happened when we, when we use the logic of selecting or putting the object which has maximum weight. Now, let us look at another scenario of filling the knapsack with which has maximum profit. So again, profit P1, object 1 has maximum profit. So we will start filling up with the maximum profit. So when we start filling up with maximum profit, what we will have? We will have the same, the first row, same thing we will get, because profits are object 1 has higher profit, object 2 next, object 3 the last. So this is nothing but same as taking objects, what we call the weights, because in this case we have the same weights. Weights are and profits are increasing. And let us take another scenario. Let us try to take the scenario of filling the the knapsack from decreasing weight. So what we will do is we will use object 3, it's lowest, fill everything up with object 3. So when we fill everything of object 3 with in sack, what we will get is fraction is 1. So 20 minus 10 is 10. So 10 will be remaining. Then this 10 remaining, next is object 2. So since 10 is remaining, fraction of 10 by 15 has to be filled up. So x2 will be 10 by 15. And 10 gets minus. So 0 is the weight remaining. So x1 will be 0 since nothing of object 1 is filled up in the knapsack. Now let us compute its weight. Weight will be 18 into 0, which is 0, plus 15 into 10 by 15, which will be 10 itself, plus 1 into weight is 10, which gives us 20. What will be the profit? Profit will be 0 multiplied by 20, 0 multiplied by 25, then 0 multiplied by 25, then 10 by 15 multiplied by 24, plus 1 multiplied by 15, which gives us 31 as the profit. Now, if you see, both are feasible solutions. And this, forget about the 0, 1 and 5 by 10 over here. We'll come to that later. Now, both have got fills the capacity to full extent, both the logics. But one gives the profit as 28.2, the other gives the profit 31. So, is selecting more weight, selecting objects in increasing order of weight, or selecting objects of decreasing order of weight? Which one gives us more profit? Looking at this example, we can say that selecting objects with less in increasing order of weight will give us more profit, because that is 31 profit earned. Profit earned is 31. But that is not always the case. There's another actual greedy approach to it. Now, these two are feasible solutions. But the actual greedy approach is to take the profit per unit of weight. Not to select which has more profit, or not to select which has more weight, or not to select which has less weight. It is to select the object based, the greedy approach is to select the object based on the profit per unit weight. So what we have is we will take the ratio of PI by WI. This is ratio of profit to weight, which gives us profit per unit weight. So this P1 by W1, which is 25 by 15, which gives the answer 1.39. So for object 1, the P1, the ratio of P1 by P2 is 1.39. The same way for object 2, it is P2 by W2, which is 24 by 15, which is 1.6. And the third one is P3 by W3, which is P3 is 15 and W3 is 10, so it is 1.5. Now, once we compute the ratio of profit by weight or profit for unit weight, we will select, based on this criteria, we will select the objects in decreasing from the highest, decreasing order. So, which one is highest? Object 2 has the highest profit to weight ratio, which is 1.6. So, we will select 1.6, object 2, which has the highest profit to weight ratio. That is object 2. We will select object 2. We will fill it with complete. We will fill the knapsack with complete object 2. That is 1. So fraction is 1. So x2 will be 1. So 20 minus 15 is 5. So knapsack now has 5 kgs remaining. Then, which has the next highest profit to weight ratio? Object 3. So since 5 is remaining weight, so we will fill it by 5 divided by 10. That is the fraction. 5 divided by 10 of object 3. So x3 will be 5 by 10. Now 5 by 10 will give us 5 by 10. 5 into 10 by 10 is 5 itself. So 5 kgs minus from the remaining capacity, we are left with 0. So nothing of object 1 will be filled. Nothing of object 1 will be filled. So our solution, that fraction, what we have for the solutions is 0 for x1, 1 for x2, and 5 by 10 for x3. If we compute its weight, 18 into 0 plus 15 into 1 plus 10 into 5 by 10 will give us 20. The whole of the knapsack is filled. What will be the profit earned? Profit earned will be 25, which is P1. 25, which is P1 multiplied by 0 plus 24 is the profit for object 2 multiplied by 1 plus 15 is the profit for object 3 multiplied by fraction, that is 5 by 10 will give us 31.5. And you can see that 31.5 is the maximum profit that can be earned by filling the knapsack with the fraction 1 of object 2, that is x2, fraction 5 by 10 of object 3, and nothing of object 1. So the greedy approach to solve this knapsack problem will be to use the ratio of profit by weight in decreasing order. So this is how you will be able to get the optimal solution and maximum profit. So this was the knapsack problem. Now let us look at the, let us briefly say that knapsack, there are n objects in knapsack. Each object has weight and profit associated with it. And there is a knapsack or a bag whose capacity is n. The objective is to maximize the profit earned, and the constraint is that subject to knapsack should be less than equal to the capacity of the knapsack, which is n. And fraction will lie between 0 to 1, that is x is between 0 to 1, and number of objects, that is I, each object I is between 1 to n. Greedy approach maximizes the profit if the objects that needs to be filled in the knapsack are considered in the decreasing order of the ratio of profit by weight. So this is what is the knapsack problem. Now how to solve this knapsack problem? Let us look at the algorithm. Let us call this as greedy knapsack. And this greedy knapsack algorithm takes M and N. This M is the actual capacity of the knapsack, and N is the number of objects in the knapsack problem. Now, all the object x fraction x is considered as a fraction. It's an array now, and I represents its object. So xi, x1, x2, x3. So all the fractions are initialized to 0 for all the objects. Then u is considered. We will take a variable u, which is initialized with the capacity of the knapsack. Then for each object, we try to check if the weight of the object is greater than the u. Now here u is initialized to capacity of the knapsack, but u actually represents remaining capacity. So initially, the remaining capacity is the full capacity, that is m. So we check if the weight of the object is greater than remaining capacity. If it is greater, we cannot put that object, so break. Else, complete object is put in the knapsack. So fraction of that object I will be 1. And what will be the remaining capacity now? The previous remaining capacity minus the weight of the object, which is added to the knapsack. So this gives us the remaining capacity u. So u is actually the remaining capacity. So this goes on is done for all the n objects. And lastly, we check if I is less than n. If there is some object remaining, then we will put that fraction, that is the remaining capacity, divided by weight of the capacity will be its fraction. And all the rest of the elements, not elements, the rest of the objects, their fraction will be 0. So this is how greedy knapsack will work. Now, the assumption for this algorithm is that the array which stores the knapsack is sorted in descending order of profit by weight ratio. Only then this greedy knapsack algorithm will work and gives us the maximum profit or optimal solution. So it is assumed that the array is already sorted, array which contains the objects, their profits and their weights are already, that array is already sorted based in decreasing order based on the profit by weight ratio. So this is how this greedy knapsack will work. Let us look at the time complexity. Obviously, for this for loop runs for n number of times, so it is O of n. This entire for loop will also run for O of n times, so it is n times, so it is O of n. And other statements are primitive statements. So the entire complexity of this knapsack, that is greedy knapsack, is O of n. Remember why I'm saying greedy knapsack, because knapsack problem can be solved using other approaches also. That is covered in the later topics in dynamic programming, in branch and bound. So those are covered in the later topics. So that is why I'm telling you the knapsack problem using greedy approach will be taking O of n. But here the assumption is that the array which contains the objects is already sorted in descending order. So sorting obviously will take some time. So anyway, that sorting is not part of the greedy approach of knapsack. That is why we're saying O of n. So this is what is the knapsack problem. Now let us look at job sequencing with deadlines. That is the another problem that can be solved using Knapsack. Oh, sorry, not Knapsack. Sorry, another problem that can be solved using a greedy approach or greedy method. Now, as the name suggests, job sequencing, it's nothing but to process some jobs. Let us consider there are n number of jobs. As we had n number of objects on Knapsack, same way n number of jobs. But with each job, there is some profit is associated. That is, if that job is completed, we get so much profit. Along with that, there is a deadline also associated with the job. That is, a job has to be completed within some deadline. For example, if we take this, my class, what is going on. Now, a job is a class. That's my job, to take a class. What is the deadline I have? Deadline I have is till 1 p.m. because this class ends at 1 p.m. Now, how much I cover in this or how much I complete, we are not bothered about that. How much syllabus I complete, how many topics I take, I'm not bothered about that. My job is to take a class. The same way there is a job, this is a process that has to. That process has to be completed till a deadline. I cannot move beyond this deadline. And there is a profit associated. If I complete that job, I get some profit. Now, let us assume that we have 4 jobs. P1, P2, P3, P4 is the profits for job P1, P2, P3, P4. So 100, 10, 15, and 20. Then each one has its deadline associated. That is 2, 1, 2, 1. That is what for each deadline for each job. Now this deadline, it doesn't have any weights. Let's consider it's 2 a.m., 2 p.m. like a time, some time, 2 minutes, 3 minutes, 1 minute. So there is a deadline that a unit of time to which our job has to be completed. So let us fill this up in a table here. Now, there are certain constraints here. Constraints are each job to complete will take a unit of time. So here, J1 job deadline is 2 means it doesn't mean that it will take 2 units to complete. J1, J2, J3, J4 takes 1 unit to complete, but it should be completed by in some timeline before till 2 units. We will come to that part. We will use a timeline and we will look at it. Then only one machine is available to process these jobs. So if job 1 is getting processed, at that same time job 2 cannot get processed. So there's only one machine available, and at a time only one job can be processed. The objective is to earn a profit. So if it can be completed by its deadline on the machine, then only a profit is earned. And feasible solutions would be a subset of these jobs, with the constraint that those jobs are completed within its deadline. So how much will be the profit we get for a feasible solution if the jobs are completed by deadline? What we get is summation of the profits of not all jobs. What we have, only those jobs that can be completed by its deadline. Profit of only those jobs will give us the feasible solution. Now the problem is, that is, the objective is to earn maximum profit by completing jobs within their deadline. Job cannot exceed its deadline. So within its deadline, a job has to be completed. So again, it's a maximization problem. What we have to do is we have to maximize the profit earned. We need to maximize the profit earned. Now let us try to solve this problem. Now I have a table here which says feasible solutions and the processing sequence. That means which job is scheduled first, which is scheduled next, and what are the profit earned for that feasible solution. Now let us look at the timeline. We have the timeline till 2. So let us consider this on a scale. Let us consider this as uh, 12 noon, 0 time, 0th time, then 1 p.m., 2 p.m. So 2 p.m., 1 p.m. is the deadline. Now, job takes 1 unit of time. Job takes 1 unit of time to complete. And jobs has to be completed before its deadline. So remember that I told you deadline doesn't mean that job 2 will take 2 units of time to complete. Job 1 will not take 2 units of time. Job 2 will not take 1 unit of time. Job 3 will not take 2 units of time. Their deadlines are 2. That is, by 2 p.m. that job has to be completed. Or by 1 p.m. that job has to be completed. But all jobs takes only a unit of time to complete. Let us look at first solution. Can we schedule a job from starting, that is 0 to 1, job 1? Yes, we can. Because deadline is 2 and it is completed before its deadline. We can schedule it. Then what is the next job that can be scheduled? Can we schedule job 2? No, we cannot. Why? Why not? Because job 1 is scheduled. So job 1 is processing till 1 p.m. and job 2's deadline is 1. So job 2 cannot be scheduled here because it exceeds its deadline. It has to be completed before 1 p.m. So job 2 cannot be scheduled. Can we schedule job 3? Yes, we can schedule job 3 because its deadline is 2. And we still have a slot remaining to schedule from 1 to 1 p.m. to 2 p.m. Job 3 can be scheduled. Can we schedule job 4? No, because job 4 has deadline 1. And where job 1 is already scheduled. So job 4 cannot be scheduled. So what is the feasible solution? Job 1 and job 3. And what is the sequence of processing? First job 1 is processed, then job 3 is processed. So sequence is also same. How much profit is earned? Profit is summation of profits of the jobs which are there in the feasible solution. So J is the feasible solution here. Who are there? J1 and J3. So J1 is 100 profit plus J3's profit is 15, which gives us 115 as the profit. Now let us look at another solution, another feasible solution. Can we schedule J2 here? J2 has 1 deadline. So yes, I can schedule J2 between slot 0 to 1. 1 is the deadline, so it can be completed. Then, can I schedule J2? Yes. Sorry. Yeah, can I schedule J3? J3 deadline is 2. Yeah, I have a slot free from 1 to 2. I can schedule J3. Can I schedule J1? No, there are no slots available. J4 also no slots available. What is the feasible solution? J2, J3, job 2, J3. And what is the processing sequence? It's the same. First job 2 is scheduled, then job 3. How much profit is earned? 10 plus 15, which is 25. So if we schedule J2 and J3, only 25 units of profit will be earned. Then what is the next one? Can I schedule job 1 in the second slot from 1 to 2? Yes, I can, because 2 is the deadline and before that deadline it completes. Because it takes only 1 unit of time to complete. Can I schedule job 2 in first slot? Yes, job 2 has 1 unit of the deadline has 1, and it can be completed between this slot from 0 to 1. It can be scheduled. Job 4, 3 and 4, no, there is no slots available, so it cannot be scheduled. So what is the feasible solution? Job 1 and job 2. What is the processing sequence? Processing sequence is first job 2 is processed, then job 1 is processed. So 2 and 1 is the processing sequence. How much profit is earned? 10 for job 2 plus 100 for job 1, which is 110 is the profit earned. Now what we are doing here now, what are we doing? We are trying to just randomly pick up jobs and try to schedule it and try to find whether the profit is earned or not. But what is the greedy method of solving? Greedy method of solving this problem is to consider jobs that has high profit first. So consider jobs with a decreasing or non-increasing, decreasing order of their profit and schedule it. Schedule it such that its deadlines are not violated. So what we will do is, who has actually, this was another solution for that what do you call problem, which gave us 42 as the profit earned, total profit earned. Jobs was J3 and J4, and sequences J4 and J3. Okay. Now let us talk about the greedy approach. That is how jobs are chosen. You can read this statement, and that is what I have just now discussed or talked about. Now let us look at the greedy approach. So in greedy approach, we consider jobs in decreasing order or non-increasing order of profits, and then schedule those jobs such that we don't violate the jobs, their deadline are not violated. So what is the first job with maximum profit? It's job 1 with 100 as the maximum profit. What is its deadline? 2. So we will try, that means it can be completed till 2, not beyond 2, till 2. So we will schedule this job between 1 and 2, between a slot, in this slot of 1 to 2. We will schedule this with slot 1 to 2. So job 1 is scheduled the slot 1 to 2. Then what is the next, which job has next highest profit? Which one has next? Job 4, which has 27 as the next highest profit. So can job 4 be scheduled between slot 1 to 2? No, it cannot be scheduled. Why? Because there is already J1 job, and as well as J4 job's deadline is 1. So it cannot go beyond this one. But it can be scheduled from 0 to 1 because its deadline is 1. So if you remember, we have selected job 1 and job 4. And if you remember, we have what we did is we selected job 1 first with the maximum profit. That job 1 could have been scheduled from 0 to 1. But if we would have scheduled job 1 from 0 to 1, then job 4 would not have fit in the slot of 1 to 2 because job 4 has deadline 1. It has to be completed by this deadline. It cannot go beyond this. So what we do in greedy approach is, apart from selecting the jobs with the highest profit, or apart from considering the jobs in the decreasing order of profits, we also try to schedule those jobs from the available slots which are there from their deadline, from their respective deadline. So we schedule job J1 first, then we schedule the job J4. So J2 now cannot be scheduled because there is no space, no slot available. J3 cannot be scheduled. So profit which is earned is 27 because 27, profit which is earned is 27 summation of profits of J4 and J1, that is 27 plus 100, which is 127. And this will give us the maximum profit because of the greedy heuristic which we have used, or the greedy approach which we have used. So a feasible solution will be job 1 and job 4. And the processing sequence is job 4 and job 1, because job 4 is scheduled for job 1. Maximum profit earned is 127. So this feasible solution of J1 and J4 is the optimal solution. So this is how job sequencing, the problem of job sequencing with deadline is done. Whew. Now let us look at the greedy algorithm for this job sequencing deadline. Now this greedy algorithm, let's say greedy job, D is the deadline, J is the jobs, and N is the number of jobs. Now the jobs are obviously here also. We assume that the jobs are selected, not scheduled. Given input to the algorithm in the decreasing order of their weight. Decreasing order of their weight, that is the greedy approach we are using. Decreasing order of their weight. And then first job is selected, J. J is the actually will be the solution, feasible solution actually. Which jobs are there? So one means the first job is selected, and then from second to last job, we check if all jobs in a union of this can be completed by their deadline. If they can be completed by their deadline, then perform the union operation and add that I to the J, the solution. So then finally we will, the J which is returned or which is passed as the parameter will contain the list of the, what do you call, the jobs. Excuse me, or the sequence of the jobs that is uh, that can be processed. Now this algorithm looks very easy, but that is not the question. This is the actual, to perform this part. If all jobs in U can be completed by their deadline, then union those jobs. This is actually very complicated scenario. It's not that easy. So the actual algorithm is this, which says JS, job sequencing for deadline. And here what we have is, we have D as the deadline, J will be the solution for the jobs which are feasible, N will be number of jobs. D, that is the array as well as the job, there are none jobs. And D here, deadline means not the deadline of the jobs which are there. This is the deadline through which the jobs can be completed. Then J1, we assign 1 because the first job is selected. Here also it is assumed that the jobs are given to the jobs are given to the algorithm in decreasing order of their profit. That is sorted according to that. Then K is the variable used, we assign it to 1. For 2 to n, that is what we have seen in the easiest algorithm there. 2 to n, we will take a variable K, this is a temporary variable R which is assigned. while deadline of this job is greater than DI, the deadline which is available, and this deadline is not equal to R, means the slot is not filled, then reduce R. So we start from the last. Where did we put J1? The last slot of its deadline. Then if this is not full, we move, if this is full actually, we move to the left position. So R equal to R minus 1. We are decrementing the slots. R is just like a slot. Then if that job, if the deadline what we have for that job is less than the deadline and is greater than the actual deadline is greater than, then that means we can fill that job. So what we do, we start with K, we use another loop and we start with K and move step backwards, filling all the slots with the jobs. So at the end, when this all the filling is, so this while loop, first while loop is done to check whether a slot is available, starting from the rightmost going to the leftmost part, depending upon the deadline of the jobs. That is what is this D array. Then we will check if that can be filled, or we will check if there are other jobs that can be moved. That is what we are doing here, and then ultimately schedule the job. So this algorithm, there is a for loop. This is going to run for n times. This while loop at most will run for n times, and this is an if condition. Within this we have a for loop. So at most this also may run for n times. So while and for, these two are not inner loops, they're not nested loops, but for 2 to n and while is a nested, as well as for. For and for is nested. So this will run for n times, this will run for n times. So ultimately the complexity of this solving this is O of n square in the worst case. So O of n square in the worst case. That is the what do we say? That is the worst case time complexity of this job sequencing with deadline algorithm. So these are the two topics we have seen. With that is one of the knapsack one, and the other one is the job sequencing with deadline. Now I'll continue with the other two other topic also. That is minimum cost spanning trees. Anyway, it's 110. Oh, nobody is there in the class. Only one person is there. So anyway, I will not continue this. I'll just wind up uh, over here, and then the other two topics left out in your second unit, and that we will cover up in we'll take up in the next Thursday's class. So anyway, let us wind up now.